Now it's an interesting question. Question number 7. It says 1 mole of a ideal gas is carried through a reversible cyclic process as shown in the figure. The maximum temperature attained by the gas during cycle is. So first we have to identify on which process line would the maximum temperature lie. Since it is given it is a ideal gas, so PV is equal to RT would be there. So if we talk about say Boyle's law and the isotherms, we know that these are isotherms, and as we go away from the center or origin, the temperature increases, right? So if it is T3 and this is T1, so clearly T3 would be more than T1. So intuitively we can see that the isotherm which will be grazing this would be on the line further away, on the line BC. This would be the farthest isotherm which can touch this process. So basically this would be the maximum temperature, which means from B to this point the temperature increases, and from this point, call this point as F, to the point C the temperature decreases. So the maximum temperature would be on the process line BC, because that will be the tangent to the furthest isotherm from the origin. Now what will be the equation of this line BC? So the coordinate of point B is 1, 4, coordinate of point C is 2, 1. Arbitrary point where it is maximum, let us say it is V, P. So basically we can find the equation of line y2 minus y1 upon x2 minus x1 is equal to slope. So doing that and putting the value, we get the equation of this line, which is P plus 3V is equal to 7. Now also, how do I find this touching point? We can find it in several ways. One is by regularly finding maxima minima, right? So that is a conventional way. So let's solve with that. So wherever P is there, I can just convert this equation into one variable and then differentiate with respect to temperature. For maximum temperature, we can frame an equation for temperature with respect to either V or P and differentiate it dt by dV or dP by dV. That is one way. So let's do that. So we have the equation P. So in place of P, I can write this as what? This can be RT upon V plus 3V is equal to 7. On rearranging, we can say that RT would be equal to, this is 7V minus 3V square. Got this? So if we have to find maxima, so we can differentiate this. So one is, if I differentiate, R dt by dV will be equal to 7 minus 6V, and clearly second derivative is less than 0. So at this critical point it will be maxima. So that point V corresponding to this point F on line BC, that V will be 7 by 6. Right, and putting in PV is equal to nRT, right? So V value is 7 by 6, and if I have to find what is the maximum temperature, I can just put this value of V over here and get the maximum temperature. So we have R into T, corresponding temperature would be maximum temperature, that would be 7 in terms of in place of V I write 7 by 6 minus 3 times this is 49 by 36. So on solving, T max comes out to be, right, that comes out to be 49 upon 12R. So answer for this question would be C. Now this expression maxima you can also find by completing the squares, right? We can complete the square and hence find the maxima. Also, because xy is a constant, we can find that rectangular hyperbola equation also. X upon x1 plus y upon y1 is equal to 2. We can compare, and instantaneously with this line we can find the maxima. Now the second and the third method which I have said, you will be comfortable when you have done quadratic equations thoroughly in maths and coordinate geometry mein, physics coordinate geometry mein you have done ellipse, right? So thereafter, so anyways, at this point of time we can solve it using regular maxima minima method, and we get the answer as 49 by 12R, which corresponds to option number C.